Assalamualaikum and hello everyone. Welcome to our video on Unit 1, System of Units for Module 1 for PHY130 Microcredential course. In this video, we will discuss about physical quantity, units of a physical quantity that is basic and derived units, dimensional analysis, and unit conversion. Let us discuss about basic and derived units. To begin, let's define what is a physical quantity. In physics, physical quantity is defined as the properties of a material or system that can be quantified by measurement, such as length, volume, density, and speed. For example, you might want to know the width and length of a rectangle, or the speed of motion of an object. A physical quantity can be expressed as the combination of a numerical value and a unit. We must assign units to numerical quantities whenever we conduct measurements in order to indicate the relative size or magnitude of the property. For example, if I mention the height of the Kuala Lumpur Tower is 421, you wouldn't know how long it is since you wouldn't know what 421 represents. In fact, this measurement would only make sense if the number 421 had a corresponding unit of measurement, which is meter. The same goes with the speed of the sports car Zenvo ST1. If the top speed of the car is written without the unit 375 or 233, the numbers do not give us any meaning. Now, let us discuss types of physical quantity. There are two types of physical quantities. First, basic quantity. Second, derived quantity. Let us discuss in detail both types of quantity. Base quantity is also known as basic or fundamental quantity. It is defined as quantities that stand alone and cannot be defined in terms of any other quantity. Unit of base quantity is called base unit. As base unit help us to define more complex units in derived quantity. There are 7 base quantities. These quantities are length, mass, time, temperature, electric current, luminous intensity, and amount of substance. The SI unit for the base quantities, together with their symbols, are shown in the table. The second type of physical quantity is the derived quantity. Derived quantity is quantity that can be defined in terms of any other physical quantities. It is combination between two or more base quantities or between a base quantity and a derived quantity. Units of quantities are combinations of others' units quantity. For example, speed is a physical property that uses a unit called meter per second. Since meter per second requires the meter and second to be defined, speed is considered a derived quantity or unit. You may practice for other derived quantities as shown in the table. Let us now discuss dimensional analysis. In physics, dimensional analysis is the study of relationships between physical quantities by determining their basic quantities and units of measurement and tracking these dimensions whenever computations or comparisons are made. There are three common basic physical dimensions in mechanics corresponding to base quantities: length, mass, and time. Symbol for the dimension of length is L. Symbol for the dimension of mass is M. And symbol for the dimension of time is T. Dimension of a physical quantity in mechanics is the combinations between these three basic dimensions. Remember that an equation must have the same dimension on the left and right sides. Now, let us discuss examples of dimensional analysis problems. Example 1. Determine the dimension of speed and identify 3 units for speed from the dimension. As we know, speed is defined as length over time. Therefore, dimension of speed is L over T. The units for the speed must follow its dimension, that is, the unit of length over the unit of time. Therefore, 3 possible units for speeds are kilometers per hour, meters per second, and miles per hour. Example 2. Determine the dimension of k in equation velocity is equal to k times density. In order to solve for dimension of k, we need to rearrange the equation by moving k to the left side of the equation. We will get k equals velocity over density. As we know, density is equal to mass over volume and can be replaced in the equation. Thus, K is equal to velocity times volume over mass. We also need to replace the formula of volume into the equation. Volume is derived from area and length, and therefore the final equation is velocity times area times length over mass. Now, we have got the final equation and we may identify their dimensions. From the equation, velocity is L over T, area is just L squared, length is L, and mass is M. Substituting all the dimensions, we get the dimension of K, that is M, to the power of -1, L to the power of 4, and T to the power of -1. In the following slides, we will discuss unit of a physical quantity, the SI unit system, and the relation between SI and non-SI units. Now, let us review unit of physical quantities. From our discussion in the previous slides, a unit is a scale with which a dimension is measured. There are various systems of unit used around the world to provide unit for each dimension. For the purpose of standardization, common system of units is used in science and technology fields known as the International System or SI unit. Where unit of a physical quantity is normally stated in SI unit. If unit of a physical quantity is not given in SI unit, unit conversion is required. The table shows the SI unit for the base quantity. In relation to SI units, prefixes are helpful for expressing units of very large or extremely small physical quantities. From the tables given, we can see the SI prefix, their values and abbreviations. Each prefix represents a specific number, and that number can be expressed using a power of 10. For example, there can be a megagram, which is 10 to the power of 6, or millions grams. On the other hand, nanometer, which is 10 to the power of -9 meters, or 1 billionth of a meter. We can see that expressing the amount as a power of 10 is much more convenient than writing out the zeros in very large or very small numbers. Therefore, any physical quantity can be attached to any prefix which gives the unit a specific numerical value. Now we are going to discuss unit consistency in equations and unit conversion. As has been discussed, each physical quantity carries both value and unit. The equality symbol is used when we write a physical quantity in two different units. For example, 1 kilometer is equal to 1,000 meters. Equations are used to express relations between physical quantities. In an equation, two parameters may be added or subtracted if they have the same units. In an equation that has multiplication or division between parameters, units of parameters are treated just like algebraic symbols. Let's discuss several examples on unit consistency and conversion in the following slides. Example 3. The final velocity v of an object moving with linear motion with constant acceleration is given equation v equal p plus qt. Determine the unit of p and q. From the equation, p and qt has the same unit as v. Since v is the quantity of velocity, p and qt we have the unit of velocity, that is meter per second. The unit of q times the unit of t equals meter per second. Since t is time, we can determine the unit of q to be meter per second squared. Example 4. European men in the age group 18 to 21 years have an average height of 5 feet 4 inches. What is the height in centimeters? Given 1 inch is equal to 2.54 cm. We start the problem by converting the value 5 feet into 16 inches. We start the problem by converting the value 5 feet into 60 inches by using the conversion factor of 1 feet equals 12 inches. Adding 4 inches to 60 inches, we get 5 feet and 4 inches equal 64 inches. Adding 4 inches to 60 inches, we get 5 feet 4 inches equal 64 inches. Using the conversion factor 1 inch equals 2.54 centimeter, we can solve the question by multiplying 64 inches and 2.54 centimeter. Therefore, the final answer is 160. Therefore, the final answer is 163 cm. Example 5. Convert the density value 665 gram per liter into gram per cubic centimeter and kilogram per cubic meter. Given 1 cubic meter equals 1000 liter and 10 to the power of 6 cubic centimeters. For the first questions, 665 gram per liter is multiplied with the first conversion factor 1000 liter per 1 cubic meter to eliminate the unit of liter. The value is then multiplied with the second conversion factor 1 meter cubic per 10 to the power of 6 cubic centimeters to eliminate the unit of meter cubic. We will get the value in gram per cubic centimeter. For the second question, 665 gram per liter is multiplied with the first conversion factor 1000 liter per 1 cubic meter to eliminate the unit of liter. The value is then multiplied with the second conversion factor 1 kilogram per 1000 gram to eliminate the unit of gram. We will get the value in kilogram per cubic meter. Example 6. An undergraduate of UITM writes on Example 6. An undergraduate of UITM rides a motorcycle at 50 km per hour. Given 1.609 km is equal to 1 mile. Express the speed in meter per second and miles per hour. Using the same method as in example 5, we required 2 conversion factors to convert the unit of kilometer per hour into meter per second to get 13.9 meter per second. For the second question, we need to convert the value into miles per hour. Please apply the methods of fraction and cancelling out the units to get this answer. Now we move the last section of this video, that is precisions and significant figures. The precisions of a measured value of a physical quantity is reflected in the number of significant figures used in stating the value. Okay. Now we move on to last section of this video, that is precision and significant figure. The precision of a measured value of a physical quantity is reflected in the number of the significant figure used in stating the value. Please note that there are few rules in determining the precision of a certain values. Rule 1. A significant figure is a digit in a number. Rule 2. Leading zeros are not significant figures. Rule 3. Trailing zeros are significant figures only if spoke. Rule 3. Trailing zeros are significant figures only if so specific. In calculating very large or very small numbers, use power of 10 notation, sometimes called scientific notation. In this form, the quantity is expressed as a number between 1 to 10 multiplied by the appropriate powers of 10. For instance, the speed of light is 299,792,455 meters per second. By power of 10 notation, we can write the value with different numbers of significant figures. In two significant figures, C equals 3 to the power of 8 meters per second. In three significant figures, C equals to 2.99 to the power of 8 meters per second. And in four significant figures, C equals 2.998 to the power of 8 meters per second. Now we reach the end of the lesson. We hope you understand the lesson and enjoy the video. Please check for more videos coming soon. Till meet again. Bye.